So today I'm going to talk about the theory of locally presentable categories. And my goal will be to try to convince algebraists that you should be interested in these categories, because among the category theorists in the room, I think I don't have to do much of an effort. So I will do my best. And stop me whenever you want, if there's any doubts or comments. So let's get started. First of all, I will start with locally finitely presentable categories. And we will see where this finite appears, and maybe that we can actually generalize it to bigger cardinalities, but let's focus on these examples first. And locally finitely presentable categories are actually just a very simple categorical type of categories, which generalize the notion of an algebraic lattice. And these algebraic lattices are all over the place in algebra. So let's first give the definition and then a few examples to show that that's the case. Well, a lattice is a poset in which we have finite meets and joints. And we say a lattice is co-complete if we have all small joints, which immediately implies we have all small meets. And actually vice versa, it's also the same. But what we care is, okay, we have all small joints. A small joint is the upper bound of a small subset. So if you have a poset, P, and you have a set of objects in P, the joint of S is the upper bound of all the elements in S. And the meet is the lower bound.
I understand it's small, but small.
A small is a set. So you could have a poset with larger cardinality if you want. So let's say we have all sets, subsets have a joint. Okay, great. What else do we need?
So for a poset, you mean actually a class with an order?
Yeah. You can omit small if you want, no problem. We will get to large later on, and here is not that important. So then a directed set inside our poset is just basically a subset, a subposet in which each element, each finite amount of elements have an upper bound inside D. So if you have two elements in your D, you will have always an upper bound inside D for those two elements. So a C bigger than both. Okay, and what else? We call an element in a poset finite if for every directed set such that A is smaller than the joint of them, then there exists a D in that directed set such that A is actually smaller than one of the Ds. Okay, so this is a finite. We will get to examples and you will see this in practice. And so we say that a lattice is algebraic if it's co-complete, so we have all joints, and every object is a directed joint of finite elements. Let's go to examples and see this in practice. Let's take a group and take the lattice of subgroups of G ordered by inclusion. We have joints, just taking you take a bunch of subgroups of G and you take the subgroup generated by those, and this is the join, and the meet is just the intersection of subgroups, it's again a subgroup. So we have actually a complete lattice. Finitely generated subgroups are precisely the finite, the finite objects are precisely the finitely generated subgroups. Let's see that. Let's take a finitely generated subgroup inside a directed union of subgroups, a directed join. But the directed join of subgroups, because our subset is directed, is actually a union. It's really a union. You don't need to generate. You can choose, you can check this, because as our set is directed, if I give you a Gi and a Gj, there will be always a Gk that contains both. So in the end, this join, because our set is directed, is actually a union, and it has a subgroup structure. So we have a subgroup generated by an object inside a union of subgroups. Therefore, because for each GI, we can find one big GI. So for each little element, we have a GI in which it is included, right? And because we have a filtered set, in particular, we can find a subgroup big enough inside our directed set, which contain the n generators we have. All of this because it is a directed subset. So in particular, our subgroup is containing one of the GIs, right? So indeed, finitely generated subgroups are finite objects. And we have to check the last thing, is every subgroup can be written as a directed join of finite ones. But this is very easy because we all know that every subgroup of G can be actually written as the join of all its finitely generated subgroups. And finitely generated subgroups are finite objects. And this is indeed directed. Why is it directed? Because if I have two finitely generated subgroups, there is always a finitely generated subgroup of H which contains both. So algebraic lattices are there. We also have them for vector spaces. Same story. We take the lattice of subspaces of V ordered by inclusion with joins in the subspace generated by and meets the intersections. This is complete. Finite dimensional subspaces are the finite objects. Same argument as above. Because our index is directed, the subspace generated by all the VIs is precisely the union. And hence, as we have a finite number of elements, we can find a VI big enough that contains all of them. So our subspace is contained in one of them. And for every subspace, we have the same. It is exactly the join of all its finitely dimensional subspaces. And the indexing is again directed because two finitely generated subspaces are contained in another finitely generated subspace. Okay, we have more. We have for rings, the lattice of left ideals of R ordered by inclusion. Finitely generated ideals are finite objects. And every ideal is the join of the left, I indicate left for left ideal, the finitely generated sub-ideals. For modules, same story. The lattice of left submodules of a module over a ring. The finitely generated submodules are finite objects, and every module is the join of its finitely generated submodules. Okay, so algebraic lattices are there in almost every algebraic category that we can think of as lattices of subobjects. Well, let's go to categories. The slogan is indeed locally finitely presentable categories is just the categorical version of an algebraic lattice. Let's make this concrete. So we have co-complete lattices. We need co-complete categories. So now, before we had all joins, small joins, and here we need all small co-limits. Directed sets will become directed diagrams. Of course, our category is not a poset anymore, but we can consider diagrams with a poset shape inside our category. So you can always see a directed poset as a category in which morphisms are just given by, so we say that A maps to B. We have a morphism between A and B if A is less or equal than B. So between two objects, there would be only one morphism or maybe none if they are not related. So this is a way of seeing a poset as a category. So we have directed diagrams. Directed joins now become directed co-limits. So basically co-limits over functors with a directed diagram shape. And finite objects, and this is the most tricky one, become finitely presentable objects. And as this is tricky, I will go a bit more in detail how this goes. So remember, finite objects. A finite object in a lattice L is finite if for every directed poset such that A is smaller than the union of this directed set, then it is in particular smaller than one of them. Okay? I will give first the definition, the standard definition of finitely presentable object, and see that actually it resembles very much what we're doing here. If we have a category C, an object A in a category is finitely presentable if for every directed diagram, so our D is a poset, a directed poset, then we have that the morphisms from A to the directed co-limit are actually the co-limits from the morphisms from A to each of the elements in the diagram. What does this mean? When one can check this, is this really true with my object and my category? Well, this means for every morphism F from A to a filtered co-limit, there exists an element in the diagram such that that morphism factors through it. On that side, we have a map from A to the union, to the join. There exists a map to D. D is smaller than the join. So we have actually, this is white, this is blue. So up there, we had, and there exists a D0, and of course, this is the upper bound. So indeed, we do have a factorization. We do have such a factorization, but now in here, we only had one possible morphism between things, but in here, it's a general category, so we have to take care of what happens with morphisms. If there were such another factorization, so such an F prime 0, such that F factors through it, then they may not be the same, but they become the same before we arrive to the co-limit. So there exists a bigger, so to say, D1, such that both morphisms really become the same after moving to F of D1. Okay, so this is what it really means to be a finitely presentable object in a category. Okay, so now we have all the ingredients to define what finitely presentable category, locally finitely presentable categories are. Before I forgot, yeah, we will use this at a certain point. I won't prove it because it's not very enlightening. You just have to compute with co-limits and stuff. But every finite co-limit, a finite co-limit is a co-limit in which the diagram has has finite arrows, finite number of arrows. For example, a kernel, an equalizer. So a finite co-limit of finitely presentable objects is again finitely presentable. Nice properties, all these, they are closed under finite co-limits. Co-kernels of these objects will be, if you want to think in algebraic categories, will be again finitely presentable. Okay, so we can define what the locally finitely presentable category is. It's a co-complete category, and it has first up to isomorphism, just a set of finitely presentable objects. In here, it's important because actually locally finitely presentable categories will be large in general. They will be large, but we have a small set up to iso of objects which are finitely presentable. And every object in my category will be a directed co-limit of those ones. So somehow we have a large category which is controlled by a small one, by a small set, which is always very interesting because working with large categories is hard, but if you have a small data to work with, it makes it a lot more, you have more tools to use in order to study them. Okay, examples. The classical, it's in every possible way, sets. The category of sets with functions, it is of course co-complete. We all know how to compute co-limits in sets. I claim, and we will prove this in the next slide, finitely presentable objects are precisely the finite sets. And let's check that these two, that this satisfies actually the two conditions we have. Well, up to isomorphism, there's obviously only a countable amount of finite sets, one for each. And every set is the directed co-limit of its post set of finite subsets. This is also almost immediate, because in the end you're taking a union and quotienting out the ones that overlap. So this is so let's see that indeed finally presentable objects are the finite sets, and this is the first proof of two that there will be in the talk.
So
yeah.
You not require that the size of this diagram is finite. That this E is directed.
No.
It's a small.
No, it would be. It will be small. Yeah. I mean, if it is not, I think you can always find the co-final one, which will be. So it is. It is not, and that's why you have. I mean, in the end, you have up to isomorphism a small amount of those. So in the end, it will be quite bounded. It will be. I think it is small indeed. Yeah. Okay. Let's prove this. First, one direction. Assume X is finitely presentable with the definition we just gave. And we know X is the directed co-limit of its finite subsets. So we have the identity from X to X. X is locally presentable, and X is also a filter, a directed co-limit. So because our object is finitely presentable, it factors through one of them. So the identity factors through a finite subset. And the identity is, of course, an EP is surjective. So the second arrow will be also surjective. So we have a bijection between Y, which was a finite subset of X, and X, which immediately, of course, follows that X is finite. Okay, now the opposite. Let's take X, a finite subset, and take a directed diagram. So I indicate it like this. I'm not putting the factor. I mean, it's just to avoid a lot of notation. Basically, you can think that I is a directed set, and we have a factor from I to our category, in which the image is each of these yi's. So I just write the diagram already in my category. Okay, so I have a directed diagram and a morphism from X to Y. And I have to prove it factors through one of them in an essentially unique way. So as I said before, if we have two factorizations, they become the same farther away sufficiently in the co-limit. So for every X, we know that the image of X through F will lie in one of the images of each of the components. This is just, we have one element. It lies in the co-limit. Think of a co-limit of sets. You have a bunch of sets that glue along certain places where they overlap, but definitely our image will be in one of them. Nothing there. But X is finite, and I is a directed set. So we can find an upper bound for all these IXs such that the whole image is actually containing one of them. So we do have that F factors through one of the elements in our diagram for some G. And now we have to see that this factorization is actually unique. So assume there exists such another G prime from X to Yi, such that composing with alpha I gives us F again. Then, in particular, this is the condition I just set for every X as alpha I G prime were the same. They have the same image for every X. So, and we are in Yi. So in particular, there exists again an index sufficiently enough such that they become, I mean, this is a property of filtered and directed co-limits in sets. If you have two things that coincide in the co-limit, they will coincide at some point before. So this is what I'm saying here. And we can do this because we have a finite amount of them. So we have that the images will coincide. So we take an upper bound for all of this because we have a finite amount. And we can conclude that G and G prime become the same, not only in the co-limit, but a bit before, so to say. So we have that indeed finite sets are finally presentable. Okay. There are similar examples in which you can actually reason like in sets, for example, in posets, and the finally presentable objects will be the finite posets. It will be, there are still countably many up to ISO, and still every poset is a directed co-limit of its finite sub-posets. It's the same story, actually. You can compute direct co-limits in there as in sets, so everything works exactly the same. And the same works for graphs. Finally presentable objects are the finite graphs, and you have the same story. Let's go to more algebraic categories. Groups. It is co-complete. We know this. Finally presentable objects will be precisely the groups that have a finite presentation, mainly finite generators and finite number of equations. We will prove this in a second. That will be the second and last proof of the talk. Up to ISO, they conform a set. You have to think a little bit of cardinalities, but you have finitely generated. There are free finitely generated. There are countable amount, and then you have finite equations in each of those. So in the end, you still are in a set. You don't have a class of those. And every group is indeed the directed co-limit of its set of subgroups which are finally presented. So let's prove indeed that groups with a finite presentation are the finally presented objects in group. Let's start first with, we take a group with a finite presentation. I write it this. I could have wrote with the notation, of course, like this. Doesn't matter, but I'm interested in writing it as a co-equalizer. Why? Because I will be using the proposition that I indicated before. A small co-limits of finally presented objects are finally presented. So G is a finite co-limit. Is it a co-equalizer? It is a co-equalizer of finitely generated free groups. So it is enough, because of that proposition, to show that actually finitely generated free groups are locally finally presentable. Sorry, and then we can conclude that G is also such. So let's take a directed diagram and a finite set that will be our generators. Morphisms. We have morphisms in groups from my free generated group to H, which is a co-limit, directed co-limit. We use the forgetful functor. We know that the free functor is the left adjoint to the forgetful functor. So this is the same as morphisms and sets from X to the underlying set of H, right? Now, we know, one can check this, I won't do it today, but forgetful functor from groups to sets preserves directed co-limits. So I can take the co-limit out of the U. And now we have that X is finite, and we just proved that in sets, finite sets are precisely the finitely presentable ones. So this was the definition of finitely presentable ones. Morphisms to the co-limit, which is directed, we can take the co-limit out. And now we apply the adjunction again, and we get that this is the co-limit from factors from Fx to Hi. So indeed, a group with a finite presentation is finitely presentable. Actually, I'm saying all the time with a finite presentation is finitely presentable. In the end, you'd see where the terminology comes from. So it is finitely presentable both in the algebraic and in the categorical sense, if you want to phrase it that way. I'm trying to keep the terminology a little bit apart from each other so that this doesn't become very confusing, but it still is a bit tricky. Now the other direction. Take a finitely presentable object in groups. So first of all, we know G, it's even, I don't care even now, I just take finitely generated groups. We know it is the directed co-limit of its finitely generated groups. So again, because it is locally presentable, the identity is from G to a colimit, which is directed, so it factors through one of the elements. So there exists some factorization through one of the H's. And because the identity is surjective, the H to the G has to be as well. So we have actually an isomorphism with the finitely generated. So G is finitely generated. We are fine. But now we need a finite presentation. Let's fix a set of generators and take a set of equations presenting G. We don't know if it's finite or not. We want to show it is. Okay. For each equation, I mean, we have our set of equations, and we can take the post set of a finite set of equations. And we consider the groups generated by those. So those will be finite presentation and finitely presentable because of the first part of the proof. So we have these GIs presented as this. And in particular, we have diagrams. Just track the arrows from each GI to G. And if GI, and if you have two sets, one containing the other, so imagine EI contained in EJ, you will have a map from GI to GJ. And all those maps appearing there are precisely, are surjective, are epimorphisms, because that diagram commutes, right? So we have an epi. So all those diagrams appear there, all those morphisms, sorry, are epis. And the claim, takes a little bit of patience, but it's not hard. You can show that G is actually the colimit of that diagram. So you have all these GIs, which are finite, we have a finite presentation and arrows to G. And with a little bit of work, you prove that G is actually the colimit of those, and that actually is directed. So we have G as a directed colimit now in a different way. Before it was of its finitely generated subgroups. Now it's just of groups of finite presentation. And now we do the same trick. We take the identity, and it has to factor through one of those. And we want to prove, but now we cannot use completely a trick as above, because GI to G may not be a monomorphism. So we know it will be an epimorphism, but we want a monomorphism to conclude that G is isomorphic to one of the GIs. GIs were finite presented, so our G will be as well. But with a tiny bit of work, you can finish. We have such a factorization of the identity. So if we compose once more with Ki, you get that equality. Ki U Ki is Ki. Now, we have a commutative diagram as so. Gi to Gi, take the identity and then the structure morphism to the colimit, or take UKI to itself, and then again the structure morphism. This commutes precisely because of the equation up there. So we have two arrows to one of the elements in the colimit that become the same in the colimit, but our GIs are of finite presentation, and we have shown finite presentation is finitely presentable. So these two arrows have to coincide, that's what I said, in one of the elements before the colimit. It has to be a J big enough, and they coincide there. Well, the claim is that this Kj, the structure morphism from Gj to G, is actually invertible. And the inverse is given by this. So the structure between Gi and Gj, so the structure morphism of our diagram, and then doing U. And well, it's not that interesting. This one is direct. You just apply that KIU is the identity, and that, of course, our diagram is a colimit. So this G is a colimit. So the Kij is precisely after Kj is precisely Ki. So this is what applied there. The other one, you have to see this one is the identity. we compose with the structure 1. We unravel. So Kij, Kj is Ki. And now this we have shown up there that that's the identity of Gi, right? And so we are left that this is equal to that. But those Kij, as I pointed out before, were epimorphisms. So this implies that indeed these two are, that this is the identity and therefore it's invertible. And we conclude G is isomorphic to Gj, which had a finite presentation. Okay, it's a tiny bit technical, but I wanted to show one of the proofs because actually this proof almost works for every single algebraic category we can think of, which are, I'm thinking now of varieties of finitary many sorted algebras. And I will explain what this is. But for people a bit familiar with model theory or with universal algebra, things will come to, will sound familiar. So indeed, finitely presentable objects are the algebras presented by a finite number of generators and a finite number of equations, like in groups. And I want to analyze these particular cases because it will give a huge amount of categories that we work with in algebra and in many other fields, actually logic and so forth. So let's introduce varieties of algebras. We fix a set, which is a set of sorts. We call it that way, but it's just a set. And we call it the set of sorts. An S-sorted signature is a set sigma, which we call the set of operation symbols, together with an arity function. To each element, to each operation symbol, we have a finite word in the alphabet S, which is just a finite number of elements of S, and then an element in S apart. One is the sort of variables, and the other is the sort of the result. This sounds all very abstract. With the examples, it will be much more clear. And we denote it like this: an operation S1 times Sn to S. And if we don't have any, so if the finite word in the alphabet S, so if the sort of variables is empty, then we just don't put anything. We just do 2 points and the arrow. It's normal, just standard notation. Okay, and what is an algebra of signature sigma? It is an S-sorted set. S-sorted set is just a family of sets indexed by S, nothing very special. It's an S-sorted set with an operation, with somehow we are really given a meaning to the operation which was abstractly defined before, which is for every sigma, for every operation of arity S1 times Sn to S, we give really a function of AS1 times to ASN to A of S. These are sets, and this is a function. So in particular, of one arity, it will be really a function between sets. Okay, this is an algebra, and we have morphisms of algebras, which is just basically morphisms of S-sorted sets that preserve the operations. So for every sigma, we can first apply the operation in A, and then apply the f of S, because the operation lies in the sort S, the result. Or you can apply f of S1 to X1 and to on each sort, and then apply the operation in B. Okay, because what we are is sending sorts of A, two sorts of B. It's let's see an example. Yeah.
Do you mean by operations? Do you mean a map? Or?
A map, yeah, just a map. It's really the terminology because signatures as the set of operations. So, but it's really just a map of sets. And we denote by alg sigma, just the category of algebras. Examples. I take a set with one object, and I take an operation, a of two arity. We just take sort, but we only have one, so we don't have to choose much. Takes the sort with this just from 2 to 1. The algebras are the magmas. Why? Remember, an algebra was, for each sort, we give a set. And then we give an interpretation of the operation. And magmas are just sets with a binary operation. We don't have any more conditions, so this is the category of magmas. Another example, which is actually interesting for theoretical and computer science or for logic. Let's take a three-sorted algebra. So S will have 3 elements: input, state, and output. And we have 3 operations. We have I, which is actually initial state. We don't have nothing, and we assign a state. N, which is the operation next state. We have a state, an input, and we get a state. And O is the output. I give you state, and it gives me an output. And actually, the algebras is the category of deterministic sequential automata, which is precisely giving 3 objects, a set of inputs, a set of outputs, and a set of states. And then the operations are, I is giving the initial state. It's fixed because we go from the empty somehow, so it's just giving 1 element in S. Then we have the operation next step, this S times I to S, and the output. It gives you a state, and it gives you an output. So this is an automata. Okay. And now we say, okay, we have operations, but we are not putting any type of axioms on them, right? So I cannot say this operation should be associative. You need an equation to express that. So this is what varieties of finitary algebras will do. So far we have just algebras, no restriction. We want to put restrictions to that, equations. So we have a signature of sorts S, and just take X and a sorted set. I want to say, okay, in order to put forth equations, we want to put to write terms, right? We want to say, okay, this term equals this term. So first we have to introduce what a term is. So that's what we do here. What the set of terms over X, so X will be our variable, so to say, is the smallest S sorted set. So we have for each sort, we have a set such that, first of all, the X's are there, are our variables, okay? And we formally add for every operation we have in the signature and every element in our terms of the convenient sort, we do have a formal element, which is just the operation applied to those terms. But this is all formal. We are not imposing anything here. I just say it's like a free algebra, if you want. I give you X, and I give you operations, and I basically add what it could be adding those operations to the whole story. But this is completely formal. And observe this is a sigma algebra, because it's an S-sorted set, and we have an interpretation of the operations is precisely this one. Okay. Now we will fix our X, so our variables will be just in each sort the numerable. But that's just and then an equation in the set of variables V is just a pair of terms in the same sort. And we write T1 equals tau1 equals tau2. So nothing very special. And when we say that an algebra satisfies this equation, if for every map from V to A, where we are giving an interpretation, basically is for every variable, we give just a term, an element in A. I just put A between brackets because I'm forgetting about it being sorted or anything. I just give an interpretation for each variable. Then we have an induced map. So once I know where each of the V's go, I can send each of the terms just because this is like a free algebra, right? So it's generated by V. So I can use all the operations, and A is an algebra. So I can generate, it immediately induces a unique arrow from the terms to A. And what I say is T1 equals T2 or Tau1 equals Tau2 in our algebra A if precisely they are sent to the same guy. Because now we do have an interpretation in A, right? A is a set, an S-sorted set. Yeah.
I missed it. You say what you mean by enumerable?
The countable, yeah. So like but you could take, I mean, in each, many times equations will be just finite. You just need a finite number of variables. So just to say, you will need always, yeah, depending on your algebra, but always the enumerable, like always from 1 to n. You may need for ones only 2, for others you may need 100, but it's just that you are never going above Aleph 0 if you want. And a variety of sigma algebras is precisely a class of sigma algebras determined by a set of equations. So if I give you a set of equations, an algebra lies in a sigma algebra lies in a class C of sigma algebra, so in a variety, if and only if it satisfies the equation. So it's basically, I take all the algebras that satisfy a set of equations, and that is called a variety of algebras. Let's go to examples. We denote them by sigma and then E to specify the equations. Groups, we are back there. Sorts, only one sort. I have 3 operations, which will be the addition, the inverse, and the 0 element, or the 1 if we use the other multiplicative notation. Variables, in this case, we only need 3 to express what we want. And you just take the axioms of defining a group, and the algebras are precisely groups. Modules over arbitrary rings. Be careful, this category is objects are Rm, where M is an R module, and then the usual morphisms of modules and rings and everything behaving nice. We have 2 sorts, ring and module. We have 8 operations, which are sum, inverse, 0, and product in rings, and then sum, inverse, 0 of the module, and then we have the scalar product. Variables, we will need for rings 3 and for modules 3. We don't need more. And the equations will be the following. We have the equations of abelian groups for the ring, the equations of abelian groups for the module, and then the ring and module structure. So you have associativity of the product of rings, distributivity, because we are not assuming commutativity anywhere, so you have both, the well behavior of the tensor product with the product of the ring. So all of this, and this gives us precisely the category of modules over rings. Another category which one may say, oh, how this is not that algebraic, but still it's a variety of algebraic. Take a small category and just take pre-sheaves or co-pre-sheaves if you want. How do we model this? Take a signature will be objects of my category. It's a set because it's a small category. And the signature will be the morphism. So we have for each morphism and 1 array operation. Formally like that. Take 1 variable for each object. We just need 1. And the equations will be ecom for composition is I impose that hx equals g of f of x every time that actually that is true in my category A. And of course the identity, the same. And the algebras are precisely this. Why? Okay, an algebra is given for every A a set, x of A, and for every operation, an operation between xa and xb, such that satisfies the equations. So we have the composition is sent to the composition and identity to the identity. So it's actually given a functor. For each A, I assign a set xa, and for each morphism, x of f. So this is also a variety of algebras. And well, let me, before I pass to the non-example, all of these varieties of algebras are all locally finally presentable. And the proof is basically the same as in groups. So immediately, all of these examples are locally finally presentable. Top, as usual, it always behaves bad, is not locally finitely presentable. I won't go into the details, but finitely presentable objects are the discrete finitely topological spaces. So a co-limit of discrete spaces is discrete. So every non-discrete space cannot be reached as a directed co-limit of discrete ones. So in principle, we cannot generate it that way. Okay, we work with finite all over the place. Why not? I mean, sometimes we want operations that are not finite, but infinitary. And you can do this in algebraic varieties, and you can do this for locally presentable categories. So a regular cardinal, what is that? So it's an infinite cardinal such that it's not the sum of less cardinals, I mean a smaller number of cardinals which are smaller than itself. The first one is Aleph 0, and Aleph 1, Aleph 2, and all the successors are also examples. Let's fix one. We are going to go through like the generalization to this cardinality of the previous definition. So a poset is lambda directed if every subset of cardinality is smaller than lambda has an upper bound. So it is actually an Aleph 0 directed poset. And because strictly smaller than Aleph 0 is finite. So that's and then we say that the category is lambda small if it has strictly less than lambda arrows. So we can talk about lambda directed and lambda small co-limits. And now the same. An object is called lambda presentable if this, you remember the co-limit could go out. So before it was just directed, now it's lambda directed co-limits that can be taken outside. And in general, we say an object is presentable if it is presentable for some cardinal lambda. And the same proposition holds. A lambda small co-limit of lambda presentable objects is again lambda presentable. Before it was Aleph 0, a finite co-limit of finitely presentable objects, it's finitely presentable. And we can define locally lambda presentable categories. So they are co-complete. They have up to isomorphism only a set of lambda presentable objects, and every object can be written as a lambda directed co-limit of lambda presentable objects. And we say it's locally presentable in general if there exists a cardinal lambda for which it is lambda presentable. Okay, so it's just generalizing the previous. And we do have examples which didn't fall in the finite case, but do fall in the higher cardinality case. Of course, all the ones we treated already, they are locally Aleph 0 presentable. Toposes, all toposes are locally lambda presentable. I say we may need bigger cardinalities. Actually, you can find for each cardinality a topos which is lambda presentable and not any of the previous. An example is if you take X, a non-compact topological space, its shifts will be locally presentable, but not locally finitely presentable. The whole point is there will be covers which are not finite and cannot be, because of non-compactness, reduced to a finite one. And that gives the trick of why this guy behaves that way. Banach spaces with contractions is locally Aleph 1 presentable, but not locally finitely presentable. Upper sigma semilattices, or well, posets with countable joints, are also Aleph 1 presentable. Because you have countable joints, you have an infinitary operation. So that's where this. And now that I've given you huge lot of examples, why are we studying this? Okay, we have many categories that fall into this. But yeah, it seems just a formal framework, but no, actually the formal framework gives us a lot of properties for these categories that are very interesting to know from your categories. So I will give a list. This one, just to keep it short, I would say every locally lambda presentable category is a reflective subcategory of a pre-shift category. Pre-shift categories are very nice because set is nice. We know all about set. And then basically almost everything carries over to pre-shifts. So the fact that our C is reflective in pre-shifts gives a lot of properties. For example, locally presentable categories are complete. We just impose that we have all co-limits, but actually they do have all limits. Now, they are well-powered, which means every object has a small poset of sub-objects. The common categories, if C is locally presentable, are also locally presentable. Those are the ones. So if C is an object in C, then this guy is just the objects are just morphisms in C over C. So they are objects like this. This is an object. And two of those, and the morphisms are just morphisms here that make diagrams commute. And the other one with the C on the left is just basically reversed to put the arrows in the other direction. These are also locally presentable. Locally presentable categories are not only well-powered, they're actually co-well-powered. So its opposite also has that property, and that's really non-trivial. Lambda, and this is very important, lambda-directed colimits commute with small limits. For example, in a locally finitely presentable, directed colimits commute with finite limits. For example, monomorphisms are preserved under directed colimits, a very strong property. Because colimits a priori don't commute with limits. So for example, you have a directed colimit of kernels is the kernel of the directed colimit. This holds in every locally finitely presentable category. In a locally presentable category, every object is presentable, not for the same cardinality. But I give you an object, I can find a regular cardinal such that the object is presentable, lambda presentable for that. So actually, every locally presentable category is the union over regular cardinals of its lambda presentable objects. If both C and C op are locally presentable, actually our category is a lattice, a complete lattice. So this is good to see, okay, I have a category, I know its opposite is equivalent to something I know very well, which is locally presentable, and I know my category is not a lattice, then it cannot be locally presentable as well, because its opposite is already locally presentable. We have the adjoint functor theorem. This is great. It gives you when a functor actually has an adjoint. If you have two locally presentable categories and a functor between them, F has right adjoint if and only if it preserves all co-limits. Of course, if it has a right adjoint, that direction is always true. But the interesting thing is back. You just say, okay, oh, this preserves co-limits. It has an adjoint. Great. The left adjoint is a bit more tricky. It has to preserve small limits and lambda-directed co-limits for some cardinals, such that both are lambda presentable. Still a bit more tricky, but very useful. They have a strong epi mono and mono strong epi factorizations. They actually fulfill the small object argument, which basically what it's saying is I give you a family of morphisms. I can cook up a weak factorization in which one side will be those morphisms closed under transfinite composition and pushouts, and then another one which is orthogonal in a certain sense. I won't go because we're a bit running out of time. But in the end is I give you any family of morphisms and I can cook up a factorization, a weak factorization. And then if C is locally lambda presentable and A is small, then factors from A to C is locally lambda presentable. So for example, you can squares in your category. It will be a game because you can play with all sorts of diagrams of shapes of A. in order to get locally presentable categories again. So many, many, many properties, and there's more. I mean, it's good to know that you actually can work with them for all this great amount of categories appearing in many fields. And I wanted to finish with explaining, okay, I have these categories, and we have a definition, but how do they actually look like? Well, there are many, many ways of finding them in nature, so to say, and let me go through some of them. So let's fix lambda a regular cardinal. The following are equivalent. 1, C is locally lambda presentable. 2, C is actually a category of functors between A and Z, which preserve lambda small limits. And this is true. I mean, this is equivalent. If you have a category of functors from A to Z that preserves lambda small limits, then it is immediately lambda presentable. And you can find such a presentation for each of them. C is a reflective full subcategory of a pre-shift category, which is closed under lambda-directed co-limits. So reflective full subcategory is that the embedding has a left adjoint. C is equivalent to a lambda orthogonality class in pre-shifts for A small. I don't want to enter much into examples, but I will give the definition of what this is. An object is orthogonal to a morphism if for every arrow from the domain to your object, there exists a unique arrow from the codomain to your object, making the diagram commute. And then if you have a lambda small set of arrows, and you take the orthogonal objects to all of them, that is a lambda orthogonality class. And actually, locally lambda presentable categories are all lambda orthogonality classes to a certain family of lambda small arrows. C is a lambda-free co-completion of a small category A. And what I mean by a lambda-free co-completion is adding lambda small co-limits to your A that may not have them. So it's basically an A star together with an embedding of your A into A star, such that A star is co-complete. E preserves all lambda small co-limits that exist, but it generates the one that didn't exist. And it is universal with this property. Mainly, if you have another more functor from A to another B, which preserves all lambda small co-limits that exist, then it factors uniquely through A star. C is equivalent to the category of models of a limit sketch. Okay, what is a limit sketch? Also this is universal algebra. A limit sketch is, the rough idea is you have a small category, and it may not have all the limits you want, but you want them like to indicate, somehow cook them up. So you give a candidate. Basically, you have your small category, you have a set of diagrams, which are the limits you would like to have. They may not exist really in A, but you just have a bunch of limits of diagrams. And then you have to each diagram a co-code. May not be the limit, but you just have a nice, and what are the models of a sketch? Is basically functors that send those limits to B to real limits in set. And this is a sketch, a model of a sketch. And the category of models of a sketch are actually the locally presentable categories. And of a limit sketch, there are also co-limit sketches, and those are not locally lambda presentable categories. And then the last one, which is very beautiful for the algebraic, from the algebraic perspective, is the categories of lambda presentable locally, the locally lambda presentable categories are precisely the categories of models of the lambda-array essential algebraic theories. Basically, we have been doing equational, we have seen varieties of algebras today. Well, this is a generalization. In essential algebraic theory, you have your operations, sigma, and your equations, as we had before. But in sigma, there will be operations that are actually not defined totally. Like the composition of morphisms can only be performed if the codomain of one is equal to the domain of the following. So that's a partial operation. So we are allowing partial operations, and then the def there gives in equations where those operations are defined. So that is an algebraic, essentially algebraic theory. And the algebras over those are precisely the locally lambda presentable categories when the lambda limits several things. The number of variables in sigma, the number of equations, the number of equations that define the partial ones, and I think I'm missing one. Well, lambda, you have to see, for it to be lambda array, it's that basically lambda quotes bounds everything you want to do. And those, the models over those guys, so the algebras over those essential theories are precisely the locally lambda presentable categories. And with this, I wanted to finish. And if you are interested in learning a bit more, you have